Okay, so today we want to have a little introduction to polar graphs. We want to be able to sort of just recognize them and understand them a little bit. It's a short lesson today. So our first one here is we have this lovely looking butterfly-like polar graph here. We want to try and read it. So in what quadrant is the graph when theta equals 0? So we have the graph of r equals f of theta drawn from 0 to 2 pi. And what quadrant is it going to be when theta equals 0? So when theta equals 0, that means that the angle is going to be pointing in this direction. The angle is pointing in this direction. If it's pointing at this direction, if we can see on this graph, the only point that crosses this particular line is the one at the origin. So here at this one, it's going to be at the coordinate 0, 0. That gets a little tricky. Where are the coordinate axes? Which quadrant are they in? Which quadrant are they in? This is a difficult, this one's at the origin. I don't know if it is in any of the quadrants. If they are, the coordinate axes are typically expected to be, this one is in the first, this one is in the second, this one is in the third, and this one is in the fourth. So just rotating around like that. So if we're at 0, 0, we're on all of them. I actually don't know the answer to that question, but it's going to be there. How about pi over 4? Pi over 4 is in this direction, isn't it? So let me just take this off. So pi over 4 is in this direction. Could be this point. Does it have to be? Discuss with the person next to you. Does it have to be at this point? Where else could it be? Could be at the origin. Where else could it be?
It could be
Zinedine, keep speaking. Let's hear Zinedine's ideas. Where do you, what, no, it's good.
What if you add 180 degrees so it's like mirrored across the x-axis?
Zinedine is saying it could be here. Is it? How could this line be pi over 4? Gully, what do you think?
Maybe the video can be the negative.
What happens if r is negative? Would that coordinate be possible? Okay, so it is actually, when theta equals pi over 4, it's going to be here. It's going to be here. We're going to have a negative value on this one. How can we figure this out? Yeah, only going to be in, when theta equals pi over 4, that's the point that I've drawn. R is going to be minus 4, so it's going to be minus 4 comma pi over 4. Yes. All right, so let's have a look at how we do it. Where does it start? When theta equals 0, where does it start? Origin. Now, what I want you to do with your paper is we're going to trace where the graph goes. We're going to trace where, oh, sorry, I was wrong. What am I doing? It is in the first quadrant. But anyway, let's have a look at tracing what the graph does. So what the graph does, it's going to start here at 0, 0. It's going to start off at 0, 0. So in this, when theta is in this quadrant, it's going to start here. Now to trace a polar graph, always make anti-clockwise rotations with your hand. Always make anti-clockwise. So put your hand up, and rotate around like that, anti-clockwise. You're going to be going in an anti-clockwise motion. Now remember, that a sine function or a cosine function is a smooth function like this. There's no sharp points to it. So you're always going to be going around in circles like this. So if we start tracing, let me just clean this off a little bit. If we start tracing in this direction, round like that, where would we go next? Which quadrant? Third. Fourth. Try it for yourself. Remember, you've got to go smoothly. So look, as you're coming in here, you've got to go round like that.
Sorry? There is no other way to do this.
No, this is going to be 4 sine 2 theta. All right, so when theta is in the first quadrant here, our graph is going to be here like this. When it's in the second quadrant here, our graph is going to be here like this. When it's in the third quadrant here, our graph is going to be here like this. When it's in the fourth quadrant, theta, our graph is going to be here like this. So here in this 3 pi over 4, it's going to be in the fourth quadrant.
So can you explain it on what else it is?
There's a few ways we can do it. We can calculate it with values and stuff, but for this particular exercise, you need to be going around in these anti-clockwise direction. So when you're coming into here, if you were to try and go down into this yellow one, notice we now go clockwise. If you were to try and come into from this direction and get into a clockwise rotation, you'd have to do like a bounce back up to get to that one. And that it doesn't bounce. The shape of the curve is like this, it's smooth, there's no sharp points. So in effect, all we can possibly do is you can see the starting point is going to be here and we're going up like that. So this is our start. We're going to be going around and coming down. At that point, we've got to keep going. We would go anti-clockwise if we wanted to make this type of a transition, and it doesn't do that. It always goes clockwise. We would make a bounce if we wanted to do this one, so it's got to be coming into here. So just try it as you go around. Just try it as you go around. You've got to go around like that. You've got to come down here. You've got to go round here. And where you see how the graph rotates. All right, have a go with this one.
Wait, so but for the last question, what would you do?
It's at the origin. We'll just put origin.
So wasn't that in the first quadrant?
I think the origin is in the first quadrant. I'm going to Google it.
Would 2 pi also be in the first quadrant?
Yeah, because 2 pi is in the next rotation. You would have to go for one single rotation. You would have to go from 0 included to 2 pi excluded. And then the next period would be 2 pi included to 4 pi excluded.
2 pi is in the origin. 2 pi is in the first quadrant.
Yeah.
Origin has to be in the first quadrant.
All right. The origin doesn't belong to any quadrant.
Yeah, so 11 pi over 12 would be the second part. I mean 11 pi over 6 by the way. I think so.
All right, should we have a look at some answers? So when theta equals 0, it's going to be here, isn't it? At 5, 0 in rectangular coordinates. That's going to be in the first quadrant. How is the graph going to go? How is the graph going to go? So if I trace this bit here, we're going to go like this. We're going to come down here. We're going to go around to there. That's from 0 to pi over 2. How do I know it's that much? How do I know it's that much? Well, these lines, so like this, we have to have something that's pointing in this direction. And it's got to be this bit down here. We have to have something pointing in this direction. What's that, pi over 3? We have to have something pointing at pi over 3. And there's nothing up here, so it's got to be this point here is where it's pi over 3. So we've got to have something here. So it's got to be this point here at the origin when we get to there. So in our second rotation, we're going to be going up here like this, down here like this, round here to there. Notice we've completed a full pattern by this point. Notice we've completed a full pattern by this point. So when we move into this quadrant, we've got to trace over this bit here. And when we move into this quadrant, we're tracing over this bit here. So 2 pi over 3 would be, it's this line here. This is 2 pi over 3. So that would be this point here. That's in the second quadrant. 5 pi over 3, that's this line down here. This is 5 pi over 3. And here at this point, there's nothing down here in this quadrant. Sorry, I've gone a bit crazy there, where's that? So where's this one going to lie? Nope. It's going to be here in the second quadrant. It's going to be that point. Okay. All right. So what are the polar coordinates when the radius is 0? So basically, we want to know what is the theta when the radius is 0. So here in this direction, this is when we are at one of our extreme points. We have this extreme point of 5, 0. We have our extreme point at 5, 0. What's theta here at this point? 0. We have another extreme point down here. What is theta here at this point? Now remember, so what's the first theta at this point? What's the first theta? Trace the graph. Trace the graph. We are going to go like this, aren't we? There. We're going to go like that. We are going to go like this. So we've got that one is going to be here. When we're coming out along there, we're going to be here. When we're coming out here, we're going to be at the origin. When we're coming out here, we've got to be down there. When we're coming out here, we've got to be back here. So this point here is at polar coordinate 5, pi over 3. Rectangular coordinate minus 3 point something, minus 4 point something. This is going to happen at pi over 3. So we are at the origin there in the middle, aren't we? What's this angle? What's this angle? This is pi over 6. This is pi over 6. What's the period between the two extreme points? Pi over 3. So we are going to have, sorry, not x, it's theta. We are going to have a 0 at pi over 6. Can we see this? Let me pause here at this point. We can see the extreme point when theta equals 0. We can see the extreme point when theta equals 0. This one here. We can see the second extreme point has to be, if we're tracing the curve around, has to be at pi over 3. Let me start this again for you guys. We see our first extreme point when theta equals 0. If we trace our curve around, we go like that. So this extreme point has to have occurred when theta is in this direction, because it's back here. This is at theta equals pi over 3. What is halfway between these two? What is halfway between these two? Pi over 6 is halfway between these two. So we are going to have our 0 at pi over 6. How long does it take us to get from one extreme point to the next? How long does it take us, in terms of theta, to get from one extreme point to the next? Pi over 3. So the zeros are going to repeat periodically at n pi over 3. So if we want to find all our solutions, our first one is at pi over 6. What's our second one going to be at? Just to make this easier, this is pi over 6 plus n 2 pi over 6. So you're going to be adding, you're going to be adding 2 each time. So the next one's going to be at 5 pi over 6. Where will the next one be? 7 pi over 6. The next one, which simplifies to 3 pi over 2. And then the last one is going to be at 11 pi over 6. Anything bigger than that is more than 2 pi. Sorry, Zinedine, can you guys be quiet? I can't hear what Gully is saying. Sorry, Zinedine. Gully.
Sir, why is cannot be the interval between the pi over 6 to pi over 3? Pi over 2. Because I think there is like no graph in this interval, right?
There is. It's in the opposite direction.
Okay.
So theta is equal to which one?
Okay, I got it.
All right. Let's skip that question for now. Why don't we go to the Google Classroom, open up the link to the GeoGebra I've shared with you. When you open it up, make a copy of it for yourself.
So why don't you teach me APPC?
So we have this graph here that we're going to play with. So what I'd like you to do is what we can do, so here on this first one, let me show you, Gordon. So I've set the first one up the way that the investigation wants us to do it. So we're going to investigate it for different values. Here's our first one, 4 sine 2 theta. And what we're going to do to begin with is we're going to change the period from 2, 4, 6, and 8. And then we're going to do 1, 3, 5, and 7, even and odd numbers, and have a look at the graphs. So when we're having a look at the graphs, I want you to use this to get used to these type of functions. I've got this slider over here that lets you move your theta around. The blue line will show you the direction theta is pointing at, and the red dot will show you where on the graph it's going to be. So as we move it in this direction, we see how it curls around to the different locations. We can see it rotating around as theta goes around in the different directions from 0 to 2 pi. And you can just trace your graph and build your familiarity with how these graphs go. Watch that rotating in clockwise circles. So then we wanted to change it up to 4. If we go up to 4, we see it going in this direction, and we can get used to just tracing the outline on the graph as we go round in different directions. So what do we notice about how many extreme points there are when it is even? Here we've got b equal to 2. So in our function, it's 4 sine 2x, or 4 sine 2 theta. b is equal to 2. When we go up to 4, so b equal to 2, how many extreme points do we have? 4. When b equals 4, how many extreme points do we have? When b equals 6, how many extreme points? What's the pattern? Well, let's try at 8.
But when it's an odd number, doesn't it stay the same?
It's times 2. It's times 2. It's times 2. All right, so when it's even, it's going to be times 2. Let's try the odd ones. So how many extreme points do we have? How many extreme points do we have? So let's watch with the odd numbers, watch how the point moves around from 0 to 2 pi when we increase theta. So let's slide theta around. Look, we go around like this. We're coming down here like that. Ooh. We're going across. Notice now, at pi, we've done a full rotation. So as we go round again, we're overwriting. So the reason when it's 3, we don't have 6, we do, but they're on top of each other. They're lying on top of each other when they're odd. So we go from 0 to pi, we rotate around the whole pattern, and then we rotate around the whole pattern again. Let's try it for 5. How many extreme points? And then watch as we go around. And we go around twice. Okay, I wonder if I can type here on my iPad. So we are going to switch over. So these ones are sine. These ones are sine functions. You can spot a sine function. You can spot a sine function a mile off. Because look at, if we think about the function y equals sine x. Think about the function y equals sine x. Well, I can't sketch that. Function y equals sine x looks like this. It starts off at 0, 0. The function y equals cos x starts off at 1. And that's what's basically going to let you identify the difference between the two. So when it's sine, we're going to start off at 0. We're going to start off at the origin when it's sine, because you're multiplying 0, whatever your radius is, by 0. Doesn't matter what the radius is. It's just going to stretch out where the maximum coordinates lie. Now, let me see if I can edit in here. No. Sorry, let me just stop sharing a second, see if that lets me have a full-size screen. I got where the word cause. Right, I made it. Let me. Okay, so notice when theta equals 0, it's starting at the extreme point. Cosine ones are going to start at an extreme point here, like this over here. But it's still following the same rules that we saw earlier. When b is equal to 2, how many extreme points? 4. What will it be when b is equal to 4? And then we can just trace this around. It's following the same pattern where it alternates side to side. That's because the sine function is alternating up and down, positive, negative, positive, negative, positive, negative. If we have an odd number, it's going to trace over itself twice. We go around here. Once we get up to pi, we've completed a full rotation. Then we'll have a second rotation on top of it. So what I'm going to ask you to do is to play with this a little bit for yourself. Now, there's a second set of functions I'd like you to also look at. And just get used to tracing it and watching the movement. Just wonder and just play with it. We don't have anything else to cover for today. So on this graph, what also I would like to look at is, let's have a look at the function f of theta is equal to, and put a constant in here. Let's try 4 minus 2 sine theta. Now on these ones, make the b value 1. And try this 2 minus 4 sine theta. So what we can do is we can go in and edit that. Where am I needing to be? I need to be in here. All right. So here in this part, we want a number in here. I'm going to put 4 minus, and then I'll use my slider. Put your b down to 1 for these. And then watch what happens as we... Sorry, let me do this 2 minus. It's more fun. There. Have a look at the graph. So notice this shape. Notice this shape. This is the heart. This is sort of heart type shape. What is the relationship between the constant I put in at the front and the value of A? What is the relationship between the constant at the front and the value of A? They're both 2. Then we get the heart shape. If the value of A is bigger, you get 2 loops in one direction. If the value is smaller, you get something that looks a bit like a circle. Play around with this for homework. Notice that cosine will go in one direction, sine will go in the other direction. You can spot them a mile off. All we have for homework today is to play with this. Change the values, play with it, get used to looking at it, be familiar with these graphs.